Let's do a problem on the specific heat. A person decides to lose weight by eating only cold food. 100 grams pie of apple pie eats 1500 kilojoules of energy when eaten. If its specific heat is 1.7 kilojoules per kilogram per degree Celsius, how much less energy is its energy component at 5 degrees than at 25 degrees Celsius? So they are asking us a question. If a person tries to eat cold food, which is instead of at 25 degrees Celsius, if the person consumes at 5 degrees Celsius, how much less energy would he be consuming, or how much less energy would he be getting compared to the pie, which gives 1500 kilojoules of energy when eaten. Let's work it out. So we know that the temperature difference is from 25 to 5 degrees Celsius. So delta T is nothing but 25 minus 5 degrees Celsius. So that's going to give us 20 degrees Celsius. So we know one formula from this chapter, that is they are telling us when the thermal energy, so that is when you are changing the heat from 5 to 25 or 25 to 5, how much energy is the difference. So that's why we are choosing this equation, that is Q is equals to mc delta T. So now let's find out how much would be the energy yield if the person eats the same 0.1 kilogram of pie, but the temperature of 5 degrees Celsius. So M is 0.1 kilogram because they said it's 100 grams of pie, so that is 0.1 kilograms, and the pie's specific heat is 1.7 kilojoules per kilogram per degree Celsius. So delta T is 20. So when you multiply, you get 3.4 kilojoules of energy. So when a person eats the pie at 5 degrees Celsius, the person gains the energy of 3.4 kilojoules. Whereas if the person really ate at 1500 kilojoules at a regular temperature, then the person would have got the energy as 1500 kilojoules. So you can see how much is the difference. So this much is the energy they would be getting by eating the cold food, which is 3.4 kilojoules. Now let's move on to the next example. Find the difference in temperature between the water at the top and bottom of the waterfall. So they want us to find out the difference in temperature, which is delta T. They want us to find out. All they gave us that the water is at a height of 50 meters. So in this, we know that the material which is and the consideration is water. So we know that it is the water which is falling. So we should know the specific heat of the water, and we could find out the specific heat of the water from the tabular column which I just showed you a few minutes back. And then we know that the water is falling from a height of 50 meters. So we already know from chapter 3 that anything at a height will have potential energy. That is what will make that object to go from certain height to reach the ground. So we know that that energy is converted into the heat energy, which is bringing the change in the temperature of the waters from certain height to certain height. So once we know that, we can go ahead with the problem, that is the potential energy, which is nothing but mgh, is equivalent of the Q, so which is the thermal energy. So now we'll equate this mgh with Q is equals to mc delta T. So now we can cancel out this m with this m right here, and g is the constant, that is acceleration due to gravity, which is 9.8 meters per second square, and height is given as 50 meters. And C is the specific heat of the water, which is nothing but 4.2 kilojoules. And delta T is the thing we need to find out. So keep delta T on the side and take the C onto the right side. So you'll be left with GH over C. So just plug in all the numbers you know, that is 9.8 times 50 divided by 4.2 kilojoules. In place of K, you put the 1000, so you get 4200. So if you do the simplification, you will get the delta T is nothing but 0.12 degrees Celsius. So the temperature difference between the water which is at a height of 50 meters to the water which is falling down the 50 meters is nothing but 0.12 degrees Celsius. Now, another example on the specific heat again. How long will a 1.2 kilowatt electric kettle take to heat 0.8 kilograms of water from 20 degrees Celsius to 100 degrees Celsius? So now we have the power of the electric kettle is given and mass of the water is given, so it is water. So now we need to get the water specific heat, okay? And then the temperature is changing from 20 to 100. So we know delta T is nothing but 100 minus 20, so which is 80 degrees Celsius. And specific heat of water is 4.2 kilojoules per degree Celsius per kilogram. And mass of the water is 0.8. So what kind of work is done in here? The work done is nothing but heating the water. Okay, so we all know the power, which is P, equals to W over T. So they are asking us to find out the value of T. The power is given. If we know the value of W, we can find out the value of T. But do we know the value of W? W is nothing but F times D or mgh. There is no force given, there is no distance given, so we cannot use that work because nothing moved. Next one is mgh. We did not raise anything high, so we cannot use that one either. But now let's see what kind of work is done in this case. The work done is nothing but heating the water up. So heating the water up, what kind of formula would you be using? That is nothing but work is equivalent of the thermal energy, which is Q. So if we know the concept, we can go ahead and do the math. So the P times T, which is P is equals W over T, and that W is nothing but the thermal energy right here. So now you write Q in place of Q, MC delta T. So delta T is nothing but 100 minus 20, you got 80. T is the thing you need to find. So mass of the water we know, C we know, delta T we know, P also is given. So just find out the value of T and you'll get 224 seconds, which is equivalent of 3.7 minutes. So it will take 3.7 minutes for that water to reach 100 degrees Celsius. Now, metabolic energy. Metabolic energy is nothing but a biochemical process. The kilocalorie, we usually see it as kcal or cal, which is nothing but 4.184 kilojoules, is the energy needed for the water, which is 1 kilogram, to raise its temperature to 1 degree Celsius. The conversion of the metabolic energy into biological work is relatively inefficient. Much of its energy is wasted as heat. Okay, so metabolic process, that's why we eat a whole lot of food, but only certain amount of it is actually converted into useful energy. So when you look at the table, which gives you some idea of if you eat one raw onion, you'll get 1 kilocalorie, 5 kilocalories of energy. If you eat dill pickle, 15, as you can see, one lamb chop, it's 420. So it means it gives you heavy feeling, so it gives you a lot of energy. Okay, so now let's do another problem based on this efficiency of the body and how do we calculate them, how do we use this metabolic energy. Okay, now let's go with the problem. A 50 kilogram girl eats a banana of 500 kilojoules. She wants to work off the energy by climbing the hill. The human body is 10% efficient. How long, how high must she climb? So A girl is eating a banana and which would give 500 kilojoules of energy. Since the body is on 10% efficient, so only 10% of this energy would be actually converted into the useful energy. So how much is 10% of 500? So we have to find out that one, which is nothing but 50. So she has to burn those 50 kilojoules of energy, which she got by eating a banana. So now she needs to do the workout of climbing right, mountain or whatever. So that's nothing but W is equals to mgh, and how much is the work done, which is 50 kilojoules. Okay, so and then the mass of the girl is 50 kilograms and G is nothing but 9.8. So if you plug in those information, then so 50 kilojoules, that is, kilo stands for 1,000, so you get that number, and you will see that the girl has to climb 102 meters to burn that 50 kilojoules of energy acquired by eating a banana. The density of material is calculated by mass per unit volume, and density is denoted by the letter D. So D is nothing but mass over volume, so D equals to M over V, and its units are kilogram per meter cube or grams per centimeter cube. And you can see the density is based on the material it is made up of rather than the size or shape of it. That's why we are not talking about gold, a cylindrical gold or a circular gold. We are not talking about that. We're just saying gold. This is the density, and lead, this is the density. So it is independent of the size or shape. It is just dependent on material it is made up of. For a rectangular box, the volume of the box is given by length times width times height. So if you have a bathtub which has a length of 1.3 and a width of 0.6 and height of 0.3, we can find out the mass of the water which is filled in this tub right here, because we know the density of the water and we can find out the volume of this tub. So we're just going to find out the mass of that water. So you find out the volume of the tub by multiplying length times width times height. So that's going to give you 0.234 meter cube. And we can find out the mass by multiplying density times volume. Density of the water is nothing but 1,000 kilograms per meter cube. And it is a standard number. Density of water is 1 gram per cubic centimeter or 1,000 kilograms per meter cube. So if you multiply that, you will get 234 kilograms. So the mass of the water in the bathtub is 234 kilograms if the dimensions are given as in the picture. Now the pressure. Pressure on a surface is perpendicular to the force per unit area. Okay, so pressure is dependent on how much force we are using on how much area. Okay, so pressure and force, these two kind of confusing physical quantities, but one is we are just using force. We are not talking about how much area we are using it on. The pressure is something you are using the force, but how much area it is being affected. So we consider that. So the pressure is capital P is equals to F over A, and its units are pascals, and do not get confused with force with the pressure. Pressure units are Pascal. Pascal is a small unit, so you usually see kilopascal, megapascal like this. So you will see like kPa. So it's nothing but 1,000 Pascal.